Hi everyone, welcome to this, do we say now, like webinar, online meetup, live stream, presentation, whatever, knowledge sharing about how to build and optimize container images for AI, machine learning and data science workloads. So that's a pretty big umbrella here. And so this is, by the way, derived from a talk I gave just last week at PyData Berlin, but this is the kind of like deeper, more advanced version. So I'm Jerome Petazzoni, and I lead the container and Kubernetes instruction and training department at Arden Labs. And so I'm here to share a bunch of container stuff with you today. So, by the way, the slides are available. You can either point your phone at the QR code there, or we're also going to try and share the URL to the slides in the chat. Usually I try to do that, but you know, it is on YouTube. If you just try to share a link in the chat, YouTube is like, who's that rando and why are they trying to spam the attendees with that weird link? So I haven't yet found a way to tell YouTube, hey, it's okay, I'm legit, I'm actually the presenter, so please let me share links with my people. Yeah, thanks to my coworkers for sending the link to the slides. The link can be helpful because you're going to find all the links to all the resources I'm going to mention today. So I'm going to dive right in because I have a lot of content. I'm just going to introduce myself in a couple of sentences. I'm Jerome Petazzoni. I've worked for 7 years at Docker from 2011 to late 2017, early 2018. And since then, I've been teaching Docker and Kubernetes. And sometimes I also dressed up as a pirate to give talks at KubeCon about database operators, for instance. By the way, if you're looking for Docker or Kubernetes training, we have an open enrollment class during the second half of October. I'm going to tell you a little bit more about that later. And first, to give a little bit of context, I'm not a data scientist. You know, like I've tinkered a little bit with some models. At some point, I was following an online class on computer vision, so I actually trained a model once and deployed it to production, you know, with some inference. But I don't consider myself to be a real data scientist. So here I'm going to give you a lot of opinions and perspectives coming from the container corner, and you might have a different opinion and perspective if you're coming from the data science corner. So I'm going to explain what we're trying to do, then I'm going to explain how to build these containers with Dockerfiles, how to optimize them, and also how to build them without Dockerfiles, because there is more in life than just Dockerfiles. If we have the time at the end, I'm also going to talk about how to containerize models themselves, you know, model parameters, and try and give some conclusions. So first, what exactly is the scope of what I want to talk about today? Why are we even putting data science stuff in containers? There are two main use cases. It's not the only ones, but the two main ones are for reproducible development environments. So I'm more like a Linux person, but I suppose that many people here today are using Macs or Windows machines. And ideally, we would like everyone to have like a consistent environment with the same versions of Python and SciPy and TensorFlow or PyTorch or etc. So that we can have the same dependencies, the same bugs. I mean, obviously, ideally, we want no bugs, but if somebody has a bug, it would be great if the rest of the team could reproduce that bug on their environment. So that's one use case. Now there is another use case, which is running code in production on Kubernetes clusters. And code here could be training models, it could be running models, as we say, so inference, or it could be notebooks like Jupyter, which can be kind of in between. So first, for development environments, if you're already using something and you're happy with it, keep using that. We say like, if it's not broken, don't fix it. So for instance, if you're using Conda, or I'm seeing some folks in the chat using NixOS and Flakes, and if you're using that, and if it works great for you, then keep using it. I'm not going to tell you, throw away your amazing environment to replace it with some new stuff. No, if it works, keep doing that. Especially because when we use containers, there is often some extra little complexity around, say, file permissions or GPU access and things like that. Now, the other big use case that we have is going to be to run in production. And here, very often, let's be honest, there's going to be something related to Kubernetes. Some of us are going to be using, I would say, raw Kubernetes, and some of us are going to use some platform on top of that. Maybe there is some Kubeflow or Knative or something like that. And so very often, the first step, if we're going to use an orchestration platform, is that we have to learn how to use it. And a little tiny anecdote story, like 7 years ago when I started to teach Kubernetes, it was pretty much in the hype cycle of Kubernetes. So I had lots of companies asking me, hey, can you help us like learning Kubernetes, that new thing, everybody's talking about it. And like, yeah, sure, okay, let's run your things on Kubernetes. Can you show me your container images? And they were like, container what? Like, yeah, you have container images, right? Because if we want to run on Kubernetes, we need images. And they were like, no, we don't have container images. Do we need that? And so very often a Kubernetes training would actually turn into a Docker training, because you have to walk before you can run, and you have to learn the basics of containers before you can orchestrate these containers in production. So very often the first step, the 0th step, is going to be, let's put our things in containers. So here I'm going to do a small, as we say, like suspension of disbelief. I want to acknowledge the fact that there are platforms where maybe you wouldn't even need to learn how to make a container image. Maybe there are platforms where you can just drop a serialized model file and the platform is going to run that for you directly. Or maybe all you need to do is run, let's say, LLMs, like existing LLMs, and maybe you can do that with Ollama or VLLM or one of the many other engines that exist out there. So here, just to be clear, I'm going to talk about the specific scenario where we did our research and the conclusion is we need to put our data science code in containers. Can you help us do that? So that's what we're going to talk about. If your scenario is just, run something like Qwen or Mistral on Kubernetes, that's not the topic of today, although I also have presentations and workshops and classes on that. But today it's really about running our own models in containers. And the example I'm going to use here is based on Whisper. Whisper is a speech-to-text model, so speech recognition, which was released a few years ago by OpenAI. And I was absolutely impressed by Whisper, because even with my thick French accent, and actually even if I speak in French, a mix of French and technical terms, for instance, if I say pour fabriquer un container, ses features principales, ça va être les namespace et les cgroup, so literally that little bit of text here, Whisper pretty impressively manages to transcribe what I said, including the technical language. And so I was like, okay, this is pretty awesome. And I built some experiments with Whisper to basically take my classes. So let's take, a recording of a maybe 4-hour, 8-hour, 16-hour class and try to turn that into a playlist. There is a result here. So if you want to see a recording of one of my classes a few years ago in a kind of very basic format. That's just the beginning of the Kubernetes class. You can see that as a kind of like a demo or showcase of the way I teach if you want. And so that's available here. And I used Whisper, part of that, to transcribe me speaking during the class basically. And that was only one part of a whole pipeline. So I needed to put that in containers. And Whisper, it's like, I wrote here, like it's actual Python code in the sense that you actually, pip install Whisper and then you run it. And ideally, if you have GPUs, it's going to use them. So we're talking like actual machine learning code here. And so my first thing was, okay, let's write a Dockerfile for Whisper. Let's try to put Whisper in a container. So why did I use a Dockerfile? Why not something else? Well, a couple of reasons. First, I worked at Docker for many years, and when I was there, like part of my job was actually to teach people how to write Dockerfiles. So I was like, okay, hopefully I know how to write a Dockerfile, but also because I'm deeply convinced that writing a Dockerfile is really easy, or rather, let me rephrase that, it's really easy to get started. Sure, when we get into the optimization part, it's going to be a little bit more complex, but getting started, honestly, if you know how to write a shell script, you know how to write a Dockerfile. Because all you have to do is take a shell script. So for instance, for Whisper, this is all I need to do, pip install. And actually, Whisper is using FFmpeg to transcode and convert audio formats. So you need to install FFmpeg. And so, I pretend that I have like an Ubuntu machine or Debian machine, and I write this 3-line script, apt-get update, apt-get install FFmpeg, pip install Whisper. You put that in a Dockerfile just by adding run in front of each line, and from on the first line to indicate your starting point, like your base image. And then you build this, and it takes maybe 5-10 minutes. It depends if you are lucky to have a really fast internet connection and really fast disks, because this is going to install a ton of dependencies and packages. You can see that the resulting image is 12 gigs, which is fairly big. But there you go, we have Whisper running in a container, and so I could include that in my pipeline, and I was happy. Now, of course, if you want to include code that you're going to, edit and change over time, then your Dockerfile gets a little bit more complicated. You put something like this, copy ... That basically means take all the code in the repo and put that in the container. And that's great, except for one little detail. When you do that, the Docker caching mechanism means that each time you change one line of code, you will end up reinstalling all the dependencies. And that sucks because in the case of Whisper, we literally have 4-5 gigs of packages to download. So that's going to take a while. And so that's going to lead us to optimize that a little bit. So if you have already written Dockerfiles, I suppose that everything I'm telling you so far feels familiar, but now we're going to get into the optimization bits. The first bit of optimization is about making sure that we don't reinstall dependencies every single time. And the way we do that is just by switching things a little bit around. So basically, I added these 2 lines in the Dockerfile. The idea is, first, we are going to install the dependencies. And to do that, we copy the requirements.txt file into the container, and then we install the dependencies using that file. This is, I think, like from what I've seen for more than 12 years since I've been, teaching Docker around and talking to teams using Docker, I think this is the first optimization that almost every team does. Make sure I don't kind of stupidly reinstall all my dependencies every single time. And this cuts your build time from like 10 minutes to 3 seconds. So that's pretty good optimization. So That's the first thing we can do, but it's still not perfect in the sense that each time we change that requirements.txt file, Docker is going to detect that and we'll need to reinstall the dependencies. Because by the way, how this works is that when you build a Docker file, Docker is kind of checking, have I done that before? And if yes, then it can reuse the result of the previous build. So, the first time you build, yes, it has to run every single line and maybe that takes some time. But the second time you build, it's like, have I done that before? Yes, okay, use the cache. Have I done that before? Yes, use the cache, and so on and so on. However, if you change your requirements.txt, even if it's a small, tiny change, like maybe you add TQDM, the super great package in Python to have nice progress bars, or maybe you bump the dependencies, you change the version of something that you're using, then that line is not in the cache anymore, and at that point Docker needs to rerun that line entirely and re-download the 4-5 gigs of packages, and that's going to take a few minutes, 5-10 minutes, even longer if your internet connection is slow. So we're like, okay, can we do better? Is there a way to tell Docker, hey, I see that you're downloading a bunch of packages here. Is there a way to not re-download everything every single time? Well, there is a way. And that way is to use a BuildKit cache mount, and it's going to look like this. So it starts looking a little bit less intuitive and a little bit more weird, compared to what we had before. So you do a run, and we have -- mount type equal cache, and then we put a target. So that basically means that directory is going to be a cache directory. So what does that mean, like a cache directory? It means two things. First, that cache directory is going to persist between builds. So the first time that cache directory is empty and pip is going to download a bunch of packages in there. Next time, maybe you change the version of TQDM or of TensorFlow or whatever. The second time, that directory will be there and populated with the downloads of the previous build, and pip is going to recognize that. It's going to be like, oh, you want to install all these dependencies, and good news, I already have most of them in the cache, so you save a lot of download time, a lot of network bandwidth, and so on and so forth. There is another big advantage with that cache directory. It will not be included in the final image. And that's good because this is just kind of like temporary download files, so you don't need them in that image. And so the result is going to be a much smaller image. Okay, I have the size a little bit later, but basically we go from a 12 gig image to an 8 gig image, much better. You might wonder, how am I supposed to know which directory to put here? How did you find out that you had to put like /root/.cache/pip? So there are multiple ways to do that. In that particular case, I happen to kind of work regularly with pip, and I know that it's putting the download cache in home.cache pip. But if you don't know, another thing you can do, for instance, and I'm going to try and show you here, I'm going to do a docker run -ti Python, for instance. Okay, give me a shell. And I'm going to do like a pip install TQDM. Okay, and now I wonder, okay, what was installed and what's changed? I leave the container, and I'm going to do docker diff, and I'm going to put the container ID here, 7AC, etc. And this is going to show me the diff between the image and the container. So all the files that have been changed in that container, and you can see, yep, we have /root/.cache/pip, but also we can see all the files that have been installed that way. So yep, that's going to be here, Python 3.11, side packages. So this little docker diff trick, that's a way to know what changed in a container, where were the files downloaded, basically, if you don't know, So If you're not building with pip, if you're using something else like UV, or if we're not building Python, but something with Java and Maven or whatever, then you can use that Docker diff trick to know where is the download cache so that I can know what target I should put in my cache mount. Okay, so cache mounts, the result is that we went, in my benchmarks, not very scientific benchmark because, it's, well, it took between 5 and 10 minutes before the optimization each time, so it's not the kind of stuff you want to run 100 times. But installing the dependencies from the cache takes about 1 minute, and most importantly, it doesn't need to download anything from the internet, so we save a lot in network traffic as well. All right. Okay, so now one thing to keep in mind is that when you use that in a build pipeline, maybe you're using GitHub Actions or GitLab or Jenkins or something like that, very often, if we use, let's say, GitHub Actions, each time you have a new build, you start in a brand new, like, empty environment. So that kind of defeats the whole point of this cache mechanism. So how does that work in that case? In that case, we will need to tweak our GitHub Actions pipelines so that at the beginning of a build, we actually download our cache, and at the end of the build, we re-upload that cache. And downloading and uploading that cache is going to be actually very fast because GitHub Actions and Docker support like this cache backend. So for instance, if it's on GitHub Actions, there is a way to kind of pull and push back that cache to GitHub Actions where it's really, really fast. If you are on AWS or some other cloud, there is a way to have the cache on S3 or on an S3 compatible object store, and that's like way faster than downloading the packages from the original repos. Okay. One little thing that I want to mention as well, I don't have like a referral code or promo code or commission or anything, but if you feel like leveraging all that, this whole cache thing, if it feels complicated, you can also use build as a service providers, and one of them is depot.dev. They have something that works pretty well, and with tiny configuration, basically your builds will be directed to their infrastructure and they will take care of saving the cache, restoring the cache, and so on to accelerate your builds. So that's also a pretty good option. All right, so the little techniques I was showing you here, like the thing about the dependencies and the cache, that reduces the build time a lot. You go from like 10 minutes to just a few seconds. So for me, that counts as a lot. But now, one thing that sometimes we want to optimize is image size. I told you earlier, my first Whisper image was 12 gigs. And then with the cache optimization, it's only 8 gigs because the temporary downloads are not kept in the final image. Is that big? In terms of images, 12 gigs, 8 gigs, what's a big image anyway? Well, I'm going to give you a completely arbitrary series of sizes, tiny, small, medium, big, huge. So for me, and that's just my personal opinion, a tiny image is going to be less than 10 megs. And honestly, it's going to be extremely rare to have tiny images. They do exist. If you have a tiny microservice in a compiled language like Go or Rust, and if it's been fairly optimized, then yeah, it's going to be less than 10 meg. But let's be honest, in practice, most container images are going to be bigger than that because maybe they are not in a compiled language, or they have actual dependencies that are much bigger than that. So that takes us to the next range, like 10 to 100 megs. That's what I would call a small image. If I see an image, 30 megs, 90 megs, that's still a small image. And that's going to be the case for small microservices in Python or Ruby, languages like that, if they have been fairly well optimized, or a microservice in a compiled language but with some actual dependencies, because the more dependencies you add, the bigger the image. So if you see an image in that size range, usually it means the person who wrote the image, like the Dockerfile and everything, did a pretty good job. The next range, medium images, 100 meg to 1 gig, we are still in perfectly okay territory. That's going to be microservices that haven't been too optimized, or monolith, like stuff with Django, Rails node without a ton of dependencies. Database images are usually in that range as well. And data science, well, honestly, it's pretty rare to have data science images in that range, because data science images will typically be in the next range just because of their dependencies. We're going to see, like, very soon, in a few minutes, that a lot of data science packages are actually really big, and so it's going to be really hard to go below the 1 gig size. So that gets us into big image territory, 1 to 10 gigs. And when you see an image, let's say like 8 gigs, it could be because it actually needs to be 8 gigs because it has these dependencies, and you can't magically make them go away. Or it could be because it hasn't been very well optimized. When I do my Docker class, we take like a small example with a very tiny hello world in C, and the first iteration, the image is like 1.5 gigs. And we're like, okay, that's kind of too much, because the binary in that image is like 20 kilobytes. So we probably can do something, better, smaller than 1.5 gigs for a tiny 20 kilobyte binary. And then, we use a bunch of techniques like multi-stage builds and static builds and et cetera, until we get to something small enough. Now we have image, like above 10 gigs, and usually above 10 gigs it's going to be what I consider huge images. And again, sometimes there are some very good reasons for these images to be that big, but what I'm going to try and show you is how we can reduce that size. So in that case, in the case of Whisper, we have an 8 gigs image, and so I thought, can we do better than that? Can we do something smaller? And if I look inside the image, I look at the site package directory where you have the Python dependencies, and I looked at the 5 biggest dependencies in that image. And what we see is that we have an NVIDIA Python package, which is 4 gigs. Okay, so this is a kind of like good news, bad news scenario. This is kind of good news if I want to run Whisper on CPU, so without GPUs, because then I think I can probably remove that package and save a lot of space. But it's kind of bad news if I actually wanted to use GPU, because now I'm like, oh crap, if I want to use NVIDIA GPUs, I need at least 4 gigs just for the NVIDIA Python package. And there isn't really much I can do, because these packages is kind of like all or nothing. I can't really go in that package and just start removing a bunch of files. I mean, some people try and do that, but I'm going to give you like a tiny anecdote. Like a few years ago, some of my friends were working with a big AI company, and they had this problem on Azure where if you were using like a really big instance, I think with H100 GPUs and with 8 GPUs, and so if you have used GPU instances in the cloud, you can start imagining how much these instances cost. Like we're talking like basically like dollars per minute. Basically, apparently, to the best of our understanding, the teams at Azure, at Microsoft, thought it would have been a good idea to kind of optimize some things in the files installed by the drivers or whatever, except it meant that the driver would only recognize the first GPU. And you're like, well, I'm paying for an instance with 8 GPUs, so please, I would like the 8 GPUs to work, not just the first one. So at the end of the day, what my friends had to do was to kind of like remove the drivers that were pre-installed on the instance and kind of reinstall the official NVIDIA driver, and that worked. And sure, it used a little bit more disk space, so our best guess was, well, maybe the folks at Microsoft were trying to optimize disk space and they tried to remove a bunch of files to make the images smaller, but that was kind of a dumb decision at the end, because it means that your very expensive instance doesn't work correctly, and it means now that your customers need to make their own images instead of using the stock image. So anyway, all that to say that, unfortunately, if we want to use NVIDIA GPUs, we won't really be able to remove that. But what if we don't need to use GPUs? Well, good news. In the case of Whisper, so as you maybe know, like when you're doing deep learning in Python, very often it's going to be either PyTorch or TensorFlow. There are other frameworks, of course, but these ones are kind of like the two big ones. And very often, if you look at the dependencies, there's going to be either PyTorch or TensorFlow. So in that case, for Whisper, it's PyTorch. And if you go and look at the PyTorch website, you're going to see installation instructions with some options of like, hey, if you want GPU NVIDIA, you go there. If you want AMD GPU, you go there. If you want CPU, you go there. And they give you commands like this, basically, if you want CPU only. Okay, so basically then you go back to your Dockerfile, you install that before installing Whisper's dependencies, and the result is pretty good because we go from 8 gigs to 3 gigs. So that's pretty good, especially if you compare to the first iteration. You know, compared to the first iteration, we went from 12 gigs to 3 gigs. We divided by 4 the size of the image. That's pretty good. So by the way, each time I'm not going to show you the entire Dockerfile because sometimes they tend to be a little bit long and verbose, but in the slides there is a link here to a repository called Whisper Files, and in that repo I've put basically all the Docker files I'm talking about. So for instance, this is the one, you know, whoops, sorry. This is the one using BuildKit caches when installing FFmpeg, and also then when installing Whisper. And so all the techniques that I'm talking about, you can find them in these Docker files, like with examples. All right. So at this point, so we have an image which is 3 gigs. So we can either call it a day, you know, like, oh, that's a good job, or we can try to go not deeper like in Inception, but smaller. And one thing that we can see is that if you look at Python images on the Docker Hub, there is the, I would say, the default Python image, and it's fairly big. It's about 1 gig. But if we look a little bit, we see 2 other variants of that image. There is an image called Slim, like Python Slim, which is 10 times smaller. And there is a Python Alpine, which is 20 times smaller. So what's the difference? Well, the Slim image has like a normal Python interpreter, no problem, but it doesn't have a compiler and development headers. It doesn't have Git. So is that a problem? Well, it depends. When you install a Python package, there's going to be 3 scenarios. Scenario number 1, we are installing what I would call a pure Python package. It's just Python code. So you don't need a compiler. You know, you pip install or UV install or whatever. Okay, you install the package and it works. End of the story. Scenario number 2, you install a package that has some native code. You know, maybe for performance reason, there is a little bit of C code that needs to be compiled, and then that C code is going to be invoked from Python. This is why, by the way, Python is so popular with data science and things like that. Like, many people think, how can you even use Python with performance sensitive stuff? You know, Python is an interpreted language, so obviously it must be very slow. Well, the thing is that most folks who are, worried about that and conscious about performance are going to use code that actually taps into native code and compile code. So when you're going to, multiply matrices and manipulate tensors and whatever, that code is going to actually be machine code, and it's going to be almost as fast and sometimes just as fast as code in C or Fortran or something like that. So when you have code like that, now the problem is that when you try to install that package, the code must be compiled, which means you need to have a compiler and you need to have the Python, let's say, SDK. Often it's a package called python-dev on your distro, so you need to have that. So if you're using Python Slim, you cannot install these packages because Python Slim doesn't have a compiler, except, well, it turns out that compiling these packages takes time, and so at some point Python added the concept of wheels. And so a Python wheel is basically a package, and there is the possibility that this package is going to be available pre-compiled for your particular architecture and Python version. Architecture, here it means, Intel AMD 64 bits or ARM 64 bits if you are on a Raspberry Pi or on an Apple Silicon chip, or if you are on a Graviton instance on AWS. So what that means is that when you, for instance, pip install SciPy, years ago, when you would do that, it would take a really long time because a bunch of things needed to be compiled. But now when you do that, pip is actually going to try and check, is there a precompiled version for that? And if there is one, it's going to download and use it, and then you don't need a compiler. And then it means, well, first the installation is going to be faster because no need to compile, but also it means that it's going to work with Python Slim because you don't need the compiler anymore. And good news, everyone, in the case of Whisper, even though it has a bunch of dependencies, all these dependencies are available as binary wheels, which means that we can install them with Python Slim, and we save 1 more gig on the size of the final image, which means now we are at 2.3 gigs. So we have divided by 5, almost 6, the size of the image. That's pretty good. Now what about Python Alpine? Because that one is even smaller. So we're like, okay, can we do something with that? Well, bad news specifically for that scenario. Alpine is based on MUSL. So what's MUSL and why did I use all the scary emojis I could find? Because MUSL is a system library. You might have heard about the C library or the system library or the glibc or GNU-C library, like all these things kind of designate the same thing. This is the library that contains all the kind of like basic C stuff like printf and malloc and all these things that virtually every program out there uses. So Alpine is a tiny Linux distribution. Not tiny in terms of how many packages are available, because it has like tens of thousands of packages just like other distros, but tiny in terms of install size. And one of the things that Alpine does to achieve the small size is that it replaces the system library, the GNU-C library, it replaces it with MUSL. MUSL, which stands for, I think, for micro, MU like micro system library. So the result is that you have way smaller images, way smaller binaries, so that's great. But the downside is that you end up having a binary incompatibility. I insist on the binary aspect of it. That means that if I take a program that I've compiled for a GNU-libc system. And by the way, when I say GNU-libc system or glibc system, it basically means every Linux except Alpine, to simplify a little bit, like CentOS, all the Red Hat stuff, Debian, Ubuntu, and Gentoo, and etc., Arch Linux, they all use glibc. So if I compile something on a, let's say, normal Linux system, and then I take that binary to an Alpine system, chances are that it's not gonna work, and vice versa. However, I can always take the source and build it on Alpine, and it's gonna work just fine. But that means you need to recompile. And since you need to recompile, it means that all the stuff about the precompiled Python will packages, that doesn't work anymore. So a few years ago, there was like almost no precompiled package, Python wheels for Alpine. The situation though is evolving a little bit. Now I would say the usual suspects, like stuff like SciPy, NumPy, Pandas, now this is available for Alpine. So if you're using that, great. But the big ones I was talking about earlier, like PyTorch and TensorFlow, they are not yet available for Alpine. Sometimes they're even like not supported at all, meaning if you just try to build them yourself, it's not gonna work. Some people get them to work one way or another, but we need like to, it's probably going to take a little bit of time until this is supported properly, which often leads us to the conclusion, in kind of a shortcut, but to say that Alpine is not great for data science just because some packages are not well supported. But that's okay. We can still use Python Slim, or we can use just a normal Python image, and we can keep Python Alpine for, I would say, non-data science workloads. All right. So the next thing we can do, what if I actually have code that builds native packages and I still want to leverage that Python Slim thing? Is there a way to do that? And yes, there is a way, and the way is to leverage multi-stage builds. Multi-stage builds, it's something which is a very classic thing if you are using compiled languages. So if you're using Rust, or if you're using C, when you're working with containers, sooner or later somebody is going to show you multi-stage builds, and you're going to be like, wow, I just divided by 10 the size of my image, this is great. So we can also do that with Python, and I'm going to give you a couple of examples. First, a kind of like dirty way of doing it is going to copy the site packages directory from the builder stage. So basically here, you use like the full Python image, the one that has the compiler and all the options and everything. You install your packages, and this is going to entail a bunch of compilation and whatnot. And then in a second stage, we say, okay, now we're going to get that site packages directory, which contains all the stuff we just built, and we're going to put that into the Python Slim image. And most often times, probably, maybe that's gonna work. So that doesn't seem very confidence-inducing, what do you mean, like maybe, probably that's gonna work? Well, it kind of depends on I would say, the consistency of the libraries between the two. So a slightly better approach is going to rely on virtual env. And that can seem very weird because usually virtual envs in Python are used when, for instance, on my dev machine, I have multiple projects, and so for each project, I have a different virtual env, so I can have different Python packages. And so, in a way, that's kind of what Docker is doing. So using virtual env in Docker seems kind of weird. It's like, why? The Docker and virtual env are kind of like solving the same problem. So why would you use them together? Well, in this example, what we do is that we create a virtual env, and the point of the virtual env is to have everything we need in one specific directory, which is going to be useful in a multi-stage fashion, because then we can take that directory and copy it over to the run stage, and that's going to be cleaner than the site package technique here. Okay, so Can we use that with Whisper? Well, we can, but since Whisper doesn't leverage native code builds, it doesn't really make a big difference. But yeah, we can, and I have some examples in the repo I was linking earlier in the slides. Now, okay, can we go farther? Can we have an even smaller image? The next thing we can look at is when you have package installation, and so in that case, I mentioned earlier, Whisper is using FFmpeg to transcode and to convert the audio files. And very often when you have a tool like that, it's going to be compiled by the package maintainers in what I call the Christmas tree mode, like the Christmas tree with all the lights and it's blinking. And so what I mean here is that imagine I'm the package maintainer for FFmpeg, and so there are people using my package. I want these people to be happy, so I'm going to give them the best FFmpeg package ever with all the codecs and all the options and everything, which means it's going to be a fairly big package with a ton of dependencies, which means that when we install that in our container, well, in that case, I think the bill is about like 500 megs. So in that case, if really my goal was to have the smallest FFmpeg possible, I could go pretty far. I could compile FFmpeg, and because I know that all I want is audio, I could disable most of the video codecs to have something smaller. If I know that I'm only going to be manipulating, like MP3 or OGG Vorbis or M4A files, I could disable a bunch of other codecs and end up with a much smaller FFmpeg install. In that case, just for fun, I was able to find somewhere a static build of FFmpeg and put that in my container, and I ended up with something that was about 500 megs smaller. Like, okay, big win. Now, I'm going to be honest with you. In that case, it was just for like my own little kind of like hobby pipeline at home, so I wasn't too concerned about getting someone's random FFmpeg build. Now, for a professional pipeline, if I had done that for a customer, I would not have used that random weird FFmpeg package, because in terms of security and supply chain, that's no good. However, what I could have done, if this had been for a customer, is reach out to the person who has built that FFmpeg and ask them, hey, would you be okay just sending me, the build flags that you've been using so that I can reproduce that FFmpeg build in my Dockerfile? And actually, I hadn't realized before, but if I remember well, there is a special command line flag with FFmpeg so that FFmpeg shows you how it has been compiled. So I think I don't even need to reach out to that person. I could just do, I don't know, FFmpeg -- show build flags or something like that, and that would tell me how to rebuild it that way. But you get the idea. The point is, do not use some random person's binaries that you find or that you found on a sketchy repo. Build these binaries yourself or get the binaries from a trusted source. Another thing we can do, I'm just mentioning it because it's really cool. Okay, in that specific scenario, it doesn't really help us because the result is not smaller, but there is a kind of like magical container repo called Nixery. And you can do something like docker run nixery.dev/shell/ffmpeg/ what else could I need? jq/curl. When you do that, it's going to connect to, so nixery.dev, it's a kind of like magical image registry. On the fly, it's going to assemble an image with the packages that you want. And it's going to take a short while. I'm a little bit worried because usually it's faster than that, but maybe something went wrong. Normally then it starts downloading that image, and that image has the packages that you want. You know what, I'm going to let it kind of crunch in the background, and hopefully in the next minute we're going to get the corresponding image. And so you can also use that when you build an image if you want any package available in Nix packages. A somewhat easy way to do that is that way. So we're basically telling Docker, hey, get /nix from the nixery.dev ffmpeg image, copy that in our image, and now we can use the ffmpeg from Nix. All right. There are other tools available, stuff like Slim Toolkit, which used to be known as Docker Slim, and they have a pretty amazing promise because they're like, hey, stop worrying about optimizing your Docker files and images, just give us your image and we're going to like optimize it, it's magic, don't worry, it works. And it sort of works. It kind of depends on what you're running. Basically, what it does is that it's going to run the image and check the files that are actually used by the container. If a file has been opened and read, yes, we're going to include it in the image. If a file has not been touched when running the container, it's going to be left out. Seems like a good idea, except for stuff that is loaded dynamically, then it kind of falls apart. And although it works in some specific scenarios, but for others, it's just going to not work. And sometimes the worst thing is that it's going to not work, but in a subtle way. You know, like you do a simple test, it works, but then in production later, there's just like a file that is using a different codec, and that codec is loaded dynamically, and so it's not in the optimized image and it failed. But you know, it's something you could try as well. So if we do a recap here on the different techniques, we started with a 12 gigs image, which, you know, with my classification, it's like that's a really big image. And we managed to go down to 1.8 gigs if we want CPU only support. So that's 6-7 times smaller. That's great. Now to put some perspective, if I want GPU optimization, and I probably want GPU optimization with Whisper, because GPU optimization with Whisper is like 50 times faster, then I go back to 6.3 gigs and I can't really do anything about it because just the NVIDIA package is 4 gigs on its own. So here, you know, sure, going from 12 gigs to 6 gigs, it's pretty nice, but it's not the huge savings that we can see in some scenarios. All right. So one little note here is that when I ran Whisper, like for my machine learning experiments a few years ago, these numbers were almost twice smaller as today. Or to say it differently, you know, today images are twice bigger. I don't know exactly why, because I rebuilt all the images recently, you know, to see like the numbers, and I made sure to use the same Python version. I wanted to make sure that this part at least wouldn't change. And yeah, I'm not entirely sure why the images are much bigger today. One of my theories is that the GPU drivers are to blame. And the first time I saw the size of the NVIDIA packages, I was like, what is going on here? How can you have a 4 gigs NVIDIA package? Like, NVIDIA, what have you been doing? You know, and it's one of the reasons, it's not the only reason, but one of the reasons is that basically every generation of GPU is completely different. Well, sure, there are some common things, but the drivers, etc., are very different. And so when you install that NVIDIA package, it has support for I don't know how many different generations of GPUs, each with their own kind of compiler in a way, because when you're going to run some machine learning code on GPUs, that code is going to be kind of like compiled for the GPU, which means that, you know, when I pip install NVIDIA, or there is actually a bunch of compilers in that package directly or indirectly. So, and for a bunch of different GPU architectures. All right. One more thing that is, I think, pretty important. In the Python world, we often talk about dry, don't repeat yourself. You know, we say like, try to not copy paste the same code 5 times, like try to maybe have a function and find a way to, you know, factor things. So how can we do that with Dockerfiles? For instance, I was talking about CPU versus GPU. Does it mean I need to maintain like, you know, multiple copies of my Dockerfile? Oh, this is a Dockerfile for GPU. This is Dockerfile with CPU. This is the Dockerfile for AMD GPUs, and so on and so forth. So one way to handle that is build arguments. It's the kind of Docker feature where once you know about it, it's great. But when you don't know about it and you discover it, you're like, oh, cool, I didn't know that. So the way this works, it's a little bit like env in Dockerfiles, but instead it's arg, and arg is going to be available only at build time. So first thing, you know, like this variable PyTorch packages, you can see I'm using it here, $PyTorch packages. It's going to be available at build time, and you can set it during the build. And so basically with one command line argument, I can change the behavior of the build here. So it means that with a single Dockerfile, I can build multiple, let's say, flavors or variants or versions of my images. And again, I have a bunch of examples in that Whisper Files repo here, you know, like not in that particular one, but I think maybe, yeah, that one. There is a variable where you can say if you want GPU or something else. And by the way, there is also a little script here to basically build all the images, you know, like all the Docker files in the repo, like build all of them so that we can compare the results and see how big the image is depending on the kind of optimization that we're using. All right, so, all right, what's next? Yeah, okay. I'm almost at the 1 hour mark, and I absolutely had to quickly pitch you about my next class. So we're in the second half of October with Alpine Labs. We are going to run 2 weeks of Docker and Kubernetes training. There's going to be 1 week, which is basically Docker and Kubernetes. You know, if you are getting started with Docker and Kubernetes, or you already have some experience, but there is just a bunch of things that seem kind of mysterious, and you want to, you know, consolidate your foundations and understand how that really works. So that's going to be week 1. And then there is a second week, which is more oriented to Kubernetes in production, when we tackle more advanced topics like RBAC and resource request and limits, like CPU and memory, a bunch of security topics, and so on and so forth. And each time the idea is that we have 5 days of class, so 4 hours of live class training. So ideally, you know, class takes place, I mean, it depends on your time zone, but ideally class takes place in the morning. Then in the afternoon, you have a bunch of labs. We give to each student a Kubernetes cluster for the duration of the class, so they can do the labs. And we also have live Q&A and mentoring sessions if you need help with the labs. So if you're interested, the links are going to be in the slides, but also maybe my friends at Alpine Labs can also send the links on the chat, just in case some folks want the information directly. And there are bundles if you take both weeks. Okay, end of our, oh yeah, and the links here, right? Great. Oh yeah, another thing I wanted to mention, you know, end of the sponsored content, so to speak. The other thing I wanted to mention is that we're going to have another live stream like this one, October 1st, I think. Basically, we haven't set the topic for that next webinar yet. So if I have like a few ideas, but if there are specific topics where you're like, hey, I would like you to talk about this or that, feel free to send the topics in the chat. And you know, if I see a bunch of people want me to talk about, I don't know, Flux or you know, how to optimize Rust images or whatever, then I can do something on that. All right, so I have a couple of more things I wanted to mention. One is what about models, the parameters and weights for the models? And the second one is there something else than Dockerfiles? So first, models. The temptation would be great to put the models in the images. I happen to have strong opinions about that, and the opinions is no, please do not. So why not? Why not put the models in the images? Well, I would say let's always, how do we say? In Star Wars, they say only a Sith deals in absolutes. So, of course, there are exceptions. If the models are really small and they never change and you never use them locally anyway, then sure, you can put them in the image. If it's a 50 megs, embedding model or something like that, fine, put that in the image. However, if we're talking about models like the ones used by Whisper, like 3 gigs, 1.5 gigs, I would not recommend to put that in the image because it's going to kind of like bloat the image. We just spent almost an hour talking about how to make the image smaller, so let's not add 3 gigs of model weights into the image now. Okay, so if we're not putting the models in the image, where are we putting them? So we have multiple options there. We can put them in a local object store. For local dev, we can use volumes, and there is an example here where we mount a cache directory, and basically what this is going to do is that the first time you run Whisper in a container, it's going to download the models it needs, but next time it's going to find this volume and use it. So you get the best of both worlds. And on Kubernetes, this is another example where we're using a volume to cache the model files, again, so that when you restart the container, it will not have to re-download that model. Something that will be very interesting for the folks working with Kubernetes is that since Kubernetes 1.31, there is a beta feature, which is not enabled by default, so you will have to enable a feature gate, so enable this feature, but that will let you mount OCI images as a volume. What that means in concrete terms is that you can put your model in an image and then mount that image. And then you might think, hold up, you just told us like 2 minutes ago, do not put the models in the image, and now you're telling us to put the model in the image, like what's going on? Well, here I'm saying we could put it in a separate image. So that means I have my application, it has an image, and then the models, the model files, I put them in a separate image. And in that image, there's going to be just the model files and nothing else. So what that means is that when I build and rebuild and re-rebuild my app, I don't need to re-include the model every single time, I kind of keep the life cycle of both images separate. So that's pretty powerful. I think that ideally that addresses the remark or question that was asked by Lucas about that. I'm exactly talking about all these train pickle files and so on. The idea is let's put that in a separate image, again, an image that just has these files, and then we can mount that in our containers. All right, now, do we have something else than Dockerfiles, to build images? And the answer, short answer, yes, but for data science it sucks. And longer answer, so if you're working with Java or Go, there are some pretty amazing tools like Jib and Co. To build container images without a container engine. Co is kind of magical, it builds your Go binary and then it kind of builds the image in a kind of very direct, optimized way. That's awesome. Problem, I'm not aware of something like that for Python. Maybe it exists, but I never heard about it. Yeah, that's not an option. Then we have something called build packs. And basically, you know, if you're the kind of person who dislikes Dockerfiles because you feel like, well, this is kind of too complicated and I don't like it. This is my code. Just look at my code and magically build an image. This is exactly what build packs do. And it works pretty great, again, for Java apps. Like recently I was doing some Spring AI stuff and I hadn't done Java since college, so I was like, whoa, I was very rusty with the Java. And I used build packs to build the image and I was like, wow, that's impressive. The resulting image is just as good as the one I was building manually, so good work. Now, for Python and data science, though, when I try to use build packs to build a Whisper image, first, it took even longer than the naive approach, and the result was an almost 30 gigs image. So more than 2 times bigger than the super basic naive Dockerfile approach. I tried to optimize things, you know, change things here and there, and I was like, no, I can't really get it to be much smaller. And each time I was doing even a small change, it would take like 5 minutes to rebuild the image. I was like, no, okay, that's not something I would recommend. Now, maybe there are other variants of build packs that work better for data science, but I couldn't find them. So there is something in OpenShift called source to image. Documentation, at least for Python apps, is not great. It seems to be maybe not maintained. I was like, wow, they're still talking about CentOS 7 and Python 3.6. That's old. So I don't know. Maybe it's still maintained, but the docs are hidden behind some paywall or whatever. Maybe if you have an OpenShift subscription, maybe you're using source to image and you can tell me if it works great for data science, but using just the publicly available information, not convincing. There are also tools like Bazel and Nix, and you know, in a nutshell, if you are already using Bazel or Nix, and if you know how to use them, and if you know how to use them to build container images, then all the power to you. You're awesome, and you should use that. But I would say if you don't know Bazel or Nix, it's probably not a good idea to learn them just to build images. You know, they are like, again, they are really great tools, but maybe not just for that. You know, like if you're just trying to you know, light up some lamps in your backyard, maybe building a nuclear reactor is not the easiest and cheapest option. So Bazel or Nix are kind of like that, extremely powerful, but pretty difficult to learn. So if you already know them, awesome, feel free to use them to build images. Otherwise, I'm not sure. The last thing I want to mention is the existence of lazy pooling. Lazy pooling, that's particularly useful for big images. The idea is that normally when you have an image, you need to completely download and unpack that image before you can start the container. With lazy pooling, not anymore. With lazy pooling, the idea is that you start the container, even if you don't have the image yet, and it's going to find a way to kind of fetch the bits that it needs on the fly. So, you know, when you access a file, it's going to find the layer and download just the bit it needs. Okay, so to be clear, to do that, you need to build your images in a special way. You can't just get a random image and say, hey, lazy pooling. No, you need to rebuild the image so that it is in a special format. And if you want to look more into that, these are the keywords that you need to put in your search engine. You know, like stargz or stargazer. That's seekable stargz. So it's basically the image layers are going to have a kind of index so that it's possible to go and fetch random files there. Okay, so this is not going to reduce the size of the image, but it's going to make it faster to start the image on a fresh node. So when you do auto scaling, for instance, you have a brand new node, it starts, and basically, this can help to start the container before the image is fully downloaded. All right, so to wrap up, as you could see, like from what I was trying to show you, my recommendation for data science in containers is to use Dockerfiles because it's fairly easy to get started. And then you can add optimizations later down the line. You know, oh, we can do some multi-stage, we can do some caching, we can do this, we can do that, but at least you can start it fairly easily. So there is no, I would say, barrier to entry. So the learning curve is pretty nice. So that's my recommendation. Are there other ways to do it? Yes. But I was not convinced. You know, like I tried, I legit tried to get my Python code to work without going through a Dockerfile. I was not very convincing. All right. So finally, a bunch of links. I already mentioned that first repo, like Whisper Files, which has a bunch of Docker files specifically to build Whisper, but it's just a Python app, so you can easily adapt that for your own app and see what works. And in a more general way, I have a repo that's called min-image, and at this point, it's min-image singular without the S. Min-image, and at this point I think I could probably rename it to like 50 Shades of Dockerfile because it has more than 50 Docker files for a bunch of different languages. So you can see there is like Rust and Python and Java and Go and C, and each time I try to show different techniques, you know, like multi-stage and BuildKit caches and blah blah blah, and compare the results in terms of image size. So that's a pretty useful repo if you're trying to optimize your container images. And last but not least, like I was mentioning, we're going to have an open enrollment class second half of October. So if you, I would say, if you like my style of teaching and you want to learn more about Docker and Kubernetes, if you're getting started or want solid foundations, week 1 is about that. If you're already comfortable with Docker and Kubernetes but want to kind of like level up with Kubernetes, check week 2. There is a bunch of advanced content there, and we have discounts if you take both weeks. That's it, and I'm going to check in the chat for some questions and remarks. There was indeed a suggestion about the size of the okay, but maybe first rewind. Yeah, okay, so there was a question about virtual env in Docker multi-stage builds. Is that considered a best practice? Okay, I wouldn't say best practice in the sense that it's pretty rare to need the native builds. So in the general scenario, general scenario being I'm using pretty popular packages, and so probably they are already compiled for my architecture, then I don't need multi-stage. However, if I'm using some more exotic dependencies, or maybe I have a more exotic architecture, like maybe I have an ARM CPU, then maybe in that case I need to do native builds, and then multi-stage could give a lot of value, a lot of optimization to me. I think I mentioned in the slide briefly, I confess that I have not surveyed the state of Python ARM binary wheels, so I don't know if the situation is like, yep, everything is there, or more like, no, it sucks, like nothing is compiled. Ooh. So if it's the former, then we don't really need multi-stage builds for Python VN. However, if it's the latter, then yes, that could help a lot. There was a suggestion about the size of the NVIDIA packages, like maybe it could be about the DLSS models. It's quite a possibility. I'm not sure because I haven't looked into details, so all I can do is kind of have theories. But at some point I was surprised also by the size of drivers on Windows. And yeah, somebody told me that's because of all the upscaling features, because you have models to do that, and the models have weights and they are part of the drivers. So in the case of the Linux packages, I don't know if it's that. honestly, we could do a whole talk about, hey, let's go into that NVIDIA package and let's see what takes up space. But I would feel a little bit bad about that for two reasons. First, it would be kind of super specific, and also, honestly, that should be NVIDIA's job. I understand that they don't have a lot of money and life is hard when your shareholders are like, give me money. But maybe they could just hire a few like really good skilled packagers and find some ways to make these packages smaller. Maybe. Because if a $1 trillion company can't do it, then who can? What else? What about Elasticsearch dense vector with vector classification? So that was maybe suggestions for another live stream. So I don't have a lot of experience with Elasticsearch dense vector. I've done recently a workshop on Spring AI on explaining like how to leverage Spring AI and Ollama and Redis stack for local processing. In a nutshell, I have complex feelings about that whole thing because the current state with Gen AI is that it's extremely difficult to run it yourself in a cost-effective way. Either like for instance, I have a GPU because I also play video games, so I bought the GPU so I could play video games. So I can use that GPU if I want to do a little bit of machine learning, and if I want to do, if I want to use like Ollama or something like that, I have the GPU, so I can use it. But let's say now that I want to run, a frontier model, like a model that has hundreds of billions of parameters. This is going to cost me, if I want to buy the GPUs, it's going to be literally hundreds of thousands of dollars. So for my personal use, or even if I'm a small to medium sized company, there is absolutely no way that this could ever be a good investment. The return of investment, I will never see it, because if I'm putting like $500,000 in GPUs and servers, think about how much I could get from OpenAI or Anthropic or Mistral or all these companies. So today, that really annoys me because I'm a big fan of having the possibility to run the things yourself. But today, with what we call these frontier models, like the really big models, it's not really possible to run them locally in a cost-effective way. So that's why when I say, hey, we're going to show you how to run and scale stuff with Ollama and your local Kubernetes cluster, I'm like, well, let's be clear. This is not for small or medium-sized companies. It's either for really big companies that have a huge need of that, or it's if your data is highly, highly, highly sensitive because you're dealing with, state secrets and military stuff or medical data, and you don't trust OpenAI or Anthropic and so on and so on. And in that case, yeah, it makes sense to run stuff locally. So yeah, all that to say that I don't really have content on Elasticsearch dense vector, but I have some on Redis stack and that stuff. Question on Zaftra. Yeah. Oh, by the way, in the meantime, that worked. It took a little while, but see, we have a container image with FFmpeg and curl and JQ, and that image is 1.1 gig, which is reasonable, for these programs. Yeah, there was a question about Zaftra. Zaftra is the name of my computer. I always try to name my computers in funny ways, and if I'm not mistaken, Zaftra means future, because when I got that machine back then, I was like, this is the future, this is a great machine. It's not anymore, because it's like, I don't know, 5 years old at this point. So, but also Zaftra is one letter away from Zaftrak, which again, if I'm not mistaken, means breakfast. And breakfast is probably the most important thing in the day. At least because if you haven't had breakfast, that nothing is important. So, you know, from that perspective, I think we can say it's the most important thing in the way. So that the name of that machine is a kind of almost a pun between future and breakfast. Yeah, that's it. That's why there is Zaftara in my prompt here. Were there other questions? Thanks. Okay, I don't see other questions, so I think that's all for today. Thanks again. We're going to announce soon the topic for the next live stream, which is going to be in 3 weeks, October 1st, I think. When I forgot the thing. I think it's October 1st. And yeah, that's it. Thanks again for joining. The replay is going also to be available, so feel free to peruse that. And I wish you a good night, evening, afternoon, morning, depending on which time zone you are. Thanks again. Bye-bye.